Okay, so again, welcome everyone. Please feel free to join the discussion. And today's paper is going to be, today's discussion is going to be led by Dan. Dan is a data scientist at Enplan, and he found a very interesting paper that actually does a thorough comparison of how different machine learning methods can assess uncertainty. So I think when reading it, I thought it was quite relevant to discussions we've had recently about different uncertainty mechanisms. So it's a good opportunity for us to see how they stack up to each other. Go for it, Dan.
Cool, thanks, Carlos. Okay, so I'll start by sharing my screen. Okay. Can you see that, Carlos?
Yes.
Great. Okay. So yeah, as Carlos said, my name's Dan. I'm a data scientist at Enplan. And yeah, this week I've chosen to talk about this paper from Google, and it talks about basically uncertainty estimation across different model types. Now that's something that I think we have talked about at Paper Club before. We've talked about post hoc calibration and plat scaling. You know, we talked about trying to understand when we can use our softmax outputs or different parts of our model as estimates of their uncertainty. So yeah, I thought it was kind of interesting paper to bring to the table to kind of continue that discussion. Cool. So yeah, just linking back to the post hoc calibration, plat scaling presentations we've done before, you know, it's kind of easy, or at least we have a solution to correct and measure calibration within our distribution of choice. And as we found in that previous paper, it's actually linked to here, this one. You know, they talk about taking out a validation set and calibrating on that validation set, which can get you to well-calibrated predictions on a test set. Now, what this paper talks about, sort of as a continuation of that, or an expansion, is to think more about shifts in distribution and using out of distribution data to more properly measure uncertainty estimates. The argument being that's possibly where you want your model to be best at telling you when it's uncertain, and that distributional shift is something we will see in the real world quite a lot. So yeah, they mentioned that here, basically that whatever you're going to be predicting, you probably will see a dataset shift at some point, whether it's, you know, throughout the year, or whether it's, you know, changing of just general changing of the use of the platform or the data that you're seeing. We are trying to be robust to dataset shift in everything that we're modeling, I'd say. So yeah, I think this paragraph is quite important for understanding where they're coming from for the rest of the paper. And from there, they go on to say, sort of codify what they're going to do throughout the rest of the paper. They talk about, yeah, this contributions paragraph mentions what they plan to do for the rest of the paper. So trying to measure whether these uncertainty estimates are actually viable for different prevalent methods of modeling, and how well calibration on in distribution stuff translates to out of distribution stuff. Okay. I think this background section's fairly self-explanatory. Apart from here, these 2 bullet points, it's worth pointing out that the out of distribution data they choose comes in 2 forms. So they have both shifted data. So say they look at MNIST later on. With MNIST, their shifts include translations and rotations, and also completely out of distribution data. So I think with MNIST they use, I can't remember what they use, we'll get onto it later, but yeah, they have these 2 strands of out of distribution data. And so the meat of the paper comes in section 3, right? And they take these selection of models, model types, and a few different metrics, and they basically try and assess how good each model type is at understanding how uncertain it is outside of the in-distribution data. So these model types are your standard deep neural network, deep neural network with post-hoc calibration, as we discussed in Paper Club before, Monte Carlo dropout, ensembles, stochastic VI, and last layer versions of the dropout and the VI as well. Cool. And they have a few metrics that they assess across these different model types. And so I think we've all encountered these metrics before, but they basically include a revisiting of these metrics, just to set the scene for what's to come. And I think the important thing to note basically is that we want these sort of calibration or uncertainty metrics to be lower, and we want them to continue to be low, even in out of distribution cases. Okay, and sorry, yeah, I'd say the meat actually comes here in section 4. So we set the scene, we've decided what models we're going to look at, and we decided what data we're going to look at. And then in section 4, they run through these data sets using all the different model types and pick out a few different plots and metrics to show and try and illustrate the points they're making. So the first data set we go through is sorry, just realized I'm not looking at the, have we had any hands up?
It's fine, we're fine.
Okay, cool. Thanks, Carlos. Okay, so yeah, the first data set that we look at is MNIST. Yeah, let's have a look at these plots and just think about what they're showing. Okay, so the top left plot has accuracy on the y-axis and shift intensity on the x-axis. So what they're doing here is rotating the images by this number of degrees to take them out of the distribution in distribution data. We can see that we're getting very high accuracy across all the model types for the in distribution data, and that drops off pretty unanimously, and at a similar rate for all the different model types, right? So hard to distinguish which one might be best from accuracy alone. But here in the plot below, we're looking at Brier score at the same time. And what we see is actually there's a much greater spread at higher shift intensities across the different model types. And we see for the vanilla model, we're getting a pretty poor Brier score, right? Our uncertainty measures are not good. And that improves across some of the calibration or correction methods, up to a sort of optimum on the MNIST data set of standard stochastic variational inference. Right, we're getting a lower Brier score across the range of shift intensity. They plot the same thing for translations, so 2 pixels up to 14 pixel translations of the data set. And you see a quite similar thing, really difficult to distinguish the models with just an accuracy metric, but looking at the Brier score as well, we see that SVI sort of trumps all of these other models in terms of knowing how uncertain it is and that uncertainty being close to correct.
If I can add, which is that these two plots, they also show something quite interesting that I think we've discussed a fair amount in Paper Club, which is that accuracy doesn't tell the whole story about a machine learning model, right? So it's like you said, from accuracy standpoint, they are pretty much indistinguishable, all models. Like that, you would be tempted to just say, well, take the simplest model because it's the one that's easier to train, but you're just getting an overconfident model, right? Instead of getting one that can be useful, that can also know what it doesn't know, not just give a confident wrong prediction, which is quite interesting in my opinion.
I suppose it does circle back to what you want from the model. If you want to just squeeze as much accuracy as you can out for the cheapest you can, then perhaps the method that you talked about, the simplest model, is what you want. But if you're trying to use your output to quantify some kind of uncertainty, then you need to look a bit deeper, right? And I think that's what the paper is trying to get at. Yes, okay. So trying to think what to talk about next. We should probably talk a little bit about, I want to call out this plot actually. So what we're looking at in this plot is the entropy across classes of the different predictions, right? And we see that for most of these model types, we've got quite low entropy for the majority of the predictions. And this is on entirely out of distribution data. Sorry, by the way, this is not shifted. It's not translated. It's not rotated. This is just completely separate data. And in a lot of these cases, the model is actually pretty confident about its predictions, which, is obviously wrong. So we'd like to squeeze, I suppose, this low entropy predictions down. And again, SVI is performing the best here. Carlos, do you think there's anything else to talk about in these plots?
I think that they're all redundant in a way that they're just trying to show that what happens when you go out of distribution, what you would expect. And I think, they talk about it a bit in the introduction. Is like, what is the result that we want? Like, what is it that we would like to see in a machine learning? Oh yeah, it's And yeah, so it's, in summary, you want a model that knows what it does not know. So like you said, in the entropy, I also found the entropy one to be the most clear one. The others are a bit obscure in my opinion. But
Fair enough.
yes, you can see that for the vanilla model, it's just always overconfident, right? Even in out of distribution data, even when it has low accuracy, whereas the SVI is flatter, and the ensembles are also flatter in the entropy in the entropy distribution. So yeah, I think it's an interesting result to stack them all one on top of each other.
Cool. Thank you.
I think if I can add, so one last observation is that if you look at temperature scaling, which is
it's a dotted red
direct
line.
Yes. So in the entropy on out of distribution, and I think it's one of the points they make in the paper is that, well, temperature scaling is supposed to be doing this calibration directly on a validation set, but what they show is that it only calibrates in distribution, which is so it's we spoke in a paper a couple of weeks ago about the epistemic versus aleatoric uncertainty. So this one is actually just quantifying the in distribution uncertainty. So it's when you do temperature scaling, you're just you're calibrating. Yes, you're only correcting for ambiguities in the data. You're not correcting to actually get out of distribution, which I found an interesting result.
Definitely.
Because that is not what they claim in the temperature scaling paper.
Yeah. Yeah, I think it makes you question the utility of this temperature scaling. It makes sense, I suppose, if you don't think you're going to see too much dataset shift, but when are we ever not going to see too much dataset shift? I think that's the question. Okay, cool. So that's MNIST. And yeah, as Carlos says, these two paragraphs are quite useful because it sort of sets the scene for the plots as to what a perfect situation might be, which is to have a low prior score across the range, and what we actually see. I found them, very easy to read and sort of comprehend. So, yeah. So they move on then to CFAR10 and ImageNet, and basically do a similar process here. So yeah, we're seeing a similar thing, right, to our model, to our graphs on the top left, these two, but with CFAR10 and ImageNet, right? And in this case, we see that actually ensembles perform well across the board in both these data sets, right? So we are retaining quite high accuracy, even with pretty serious dataset shift. Well, perhaps not high accuracy, but compared to the rest of the population, at least a competitive level of accuracy. But what's important to call out is that the calibration error stays low for ensembles in this case, and lower than the rest of the methods, right? So we can see that these green bars are the lowest in each case, and it's the same in the ImageNet dataset, right? And sorry, go ahead.
Yeah, I have well, perhaps we can get more people's opinion on this one, but so it is true that from the plots, from the median values, it seems like ensembles are better calibrated in general, which is an encouraging result, I guess, given that CIFAR10 is arguably harder than MNIST. Same for ImageNet. But the question is that statistically significant? Meaning that they did 16 types of shift, and then they compounded all the errors. So that interquartile range in the box plot is 8 samples.
That's a fair point.
So it's 8 samples, maybe more. But
is it the interquartile range that's 8 samples? Is it like the whole box plot is 8 samples? No,
so they're not showing outliers. So it's safe to assume that all the data is contained within the box plot. So the interquartile range is going to contain half the data, right? So that's going to be 8 samples. But if you see temperature scaling, it has a good significant overlap with in Cypher 10. It has a good overlap with ensembles as well. So I would say the image nets are more, the results on ImageNet are a bit more compelling, but on Cypher 10 they are a bit they're a bit odd.
Yeah, that's a fair question. I don't know. Does anyone want to weigh in on that? No. Okay. Yeah, I'm not sure at that sample size what statistically significant difference would be. I don't know. What would you like to see? Would you like to see more samples, I suppose?
I'm not sure if more samples would. So I'm not sure how many samples would make it statistically significant, but at least a p-value would be appreciated, right? Just to say we did the test and this is what we found.
Yeah.
It is still an interesting result because the ensemble that they use is arguably the simplest type of ensemble, which is just randomly initialize 5 models.
I think they say they go up to 50, but they see all of the. I'm not sure what's presented here actually. I think I'd have to look in the appendix for that. Yeah. But they say they get most of the gain from 5.
From 5. So yeah, so it's still a very interesting result, I think.
Yeah, I'd agree. That is an interesting one because they do also talk about how these plots sort of show that temperature scaling isn't very useful in shift intensity with increasing shift intensity.
So just
but
very
I think
quickly,
you're kind of right.
Yeah, just very quickly. Joao is saying that it is not 16 samples, but 16 types of corruption, which is true. Each one has 5 intensities. Okay, so it's more than 16.
Okay. 16 types with 5 levels of intensity each.
Okay.
80 different distortions.
Yep. Okay. Okay. 80 sounds healthier.
But to be fair, the 5 levels are split here, right?
Oh yeah, 16
types.
Yeah.
With 5 levels of intensity.
Yep.
So I think each of these is only 16.
Yeah. Okay.
Types. I'm not sure though.
Yep. I think that's the case. But, okay. Should we move on?
Yes, I just wanted to, I guess, say, yeah, they make a point slightly further down about temperature scaling. Where is it? Yeah. While temperature scaling helps over the vanilla method, ensembles and dropout tend to be better. So that's their argument. I think, yeah, it would be nice to have that backed up with statistical tests, like you say. But I think they're making that argument based on, the fact that this red bar is climbing a bit higher, a bit faster than some of the other methods. Cool. Okay, and this is kind of revisiting the sorts of plots we saw earlier. I don't know how far we need to go into that really. I do actually want to, I think, move on to the text model section because I think there's some interesting plots in here as well. Cool. So what they do with the text models is look at what's the data set called? The 20 news groups data set, and they use 10 of the classes as their in distribution, and the remaining 10 classes as their shifted data. They also, I think, create a data set that is completely out of distribution as well, using this, right? And so what I wanted to talk about was these plots up here, and what they are, they're histograms of entropy. And so we, the solid lines are in distribution data. These sort of thinly dashed lines are the skewed data, and the heavy dashes out of distribution. And I think what it'd be nice to see is very low entropy for in distribution data. And as we skew the data and see out of distribution, move the histogram across the plot, kind of like this, basically. We want to have the entropy low for our in distribution examples, and as we start to see data that we don't know, increase that entropy. And they sort of call out that seeing behavior like we see in the ensemble allows us to put in an entropy threshold and sort of say, when we see entropy over a certain level, perhaps in this case it's 1.8, 1.7, we know at that point we're likely to be out of distribution, and we're likely to need to do something different to what we do with our in distribution data. So yeah, ensembling makes that possible. And we can see in a lot of the other, sorry, go ahead.
Yeah, sorry, I also think that the advantage of the ensemble over the others is that you can use one threshold to take out both skewed, which I guess is what they're calling the in distribution ambiguous data, right? It's the odd ones. So not even, but the odd ones. You can, with one threshold, filter those ones and the out of distributions, which doesn't seem to be true for any of the other methods.
No, I think you're right. Yeah, the others, for this skew data, the entropy curve seems to be really quite flat. And what they do actually mention as well is that in temperature scaling, as well as in the vanilla DNN, the skewed data has a very similar profile to the in distribution data. So it would be quite hard to detect when you're in that case with an entropy threshold. Yeah.
It's also interesting here that temperature scaling seems to behave differently than in the image datasets, right? Because it is now showing high entropy for out of distribution and not high entropy for in distribution, whereas in the image datasets it was the opposite. So if you go further up to MNIST, yeah, here there was the out of distribution, there was low entropy as well, which is funny.
I suppose this is quite dependent on what you choose for your out of distribution data as well, which, I don't know, it's always a tricky mental problem for me when papers select data for out of distribution examples, because if we knew what kind of out of distribution data we'd be seeing, then I think the problem would be solved, right? But yeah, I see where you're coming from. It is interesting that the behavior is so different with this out of distribution data compared to compared to this?
Yeah, so if anything, the ensembles get the positive points for being consistent across different data sets. Unless they were handpicked for ensembles, then it's a problem.
Yeah, that's true. That is true. One thing I will mention as well is we saw really good performance for SVI, standard SVI in MNIST. Right, it was the standout one, but that didn't seem to translate to the slightly more complicated models, I suppose, of these image classification and for these text models. And they do address that briefly in their sort of wrap up. So SVI is very promising, but it's difficult to get to work on larger data sets. Now, I'm not totally sure why that might be. I don't know whether that's just the sort of complexity of training or something else, but I thought that was quite interesting. I wasn't sure why it would work for MNIST and not for these other models, these other data sets, sorry. But yeah, I think we've kind of gone through the important bits of the results section. So I'll just sort of go through what their takeaways were. They basically called out that you want to look not only at accuracy, but also at some of these uncertainty metrics to understand how robust your model is to dataset shift. They sort of warn against post-hoc calibration as a method to see how good your model is out of distribution data. And yeah, they talk briefly about some of the methods they use, but that they call out ensembles as probably your best bet, right? And that you don't need a large ensemble. You only need five models to get most of the benefit. And as Carlos says, it's quite a simple ensemble. It's just five of your standard neural nets that they've used as a vanilla model. So yeah, I think it's quite an interesting paper. Go ahead.
There's a question in the chat, which is so basically, what does the dataset shift mean in this paper, and then does it occur naturally in data? So, do you want to address that?
Sure. I guess the shift in this paper means shift in data and the distribution. So
I think I see where the confusion comes. Yeah, when they because part of the things that they do to measure dataset shift is shift the images. So they are yeah, so they are different things.
Yes, okay, right. Maybe I used the wrong word at times. No, they do say intensity of shift. I think when they refer to shift in this paper, it's this slight modification of the data in some way to get you something that's adjacent to your in-distribution data, right? So with MNIST, they've done rotations and translations with, I'm not sure what they did with CFAR10 actually. I think they did a similar thing, right?
Yeah, they did the same alterations in all data sets.
Okay, and so they've got this shifted data, which is a slight modification, and out of distribution data, so data that has been drawn from some other set that doesn't have a label, right? It's just completely separate from our training data.
Yeah, I think
I'm not sure what the question was referring to.
So I think we may have caused a bit of confusion because we use Dataset Shift because in several other papers about uncertainty, they talk about Dataset Shift, meaning that the data generating process has changed, which is something that can occur in a nature, well, in the wild, so to speak. But here, I believe that in this paper, particularly, they speak about shifting and turning the images when they speak about shift, and then they speak about out of distribution.
But I think with the shifting and turning, they're trying to simulate a sort of change in the data generating process, right? I think that's their intention.
Yes.
So these things can happen in what was the question? In the wild? Does it occur naturally in data? Yes. Shifts like that do occur naturally, right?
Yeah, the other question is, how do they get an entropy above 1? Well, the maximum value of entropy depends on the number of classes, right? So for Cypher 10, the maximum possible entropy is the natural logarithm of 10. I don't know the value, but we can calculate it quickly. So the maximum value for Cypher 10 would be 2.3 nats. So that's in theory the maximum. So yeah, so you have 2.3 there as the maximum entropy. Yeah.
Yep.
Well, we got a ton of questions in the chat.
I know, right? Brier score is not a new thing. The paper was written in 1950. Since that time, had there emerged any sort of generally agreed threshold when you can say that the model is performing well and when you should discard your predictions as rubbish? That's not something I know, to be honest.
So there is no agreed threshold on Brier score. I think it comes mostly from the fact that, well, it hasn't been used. So this sort of confidence measurement in deep networks is relatively recent. I think that the first paper we presented is from 2016 or 2015. So, but in any case, all these uncertainty metrics only make sense, or at least I think they only make sense when you are comparing several models against each other and you want to see which one has the lowest. And ideally, you would go to a Brier score of 0, but it's a similar question of how would you say how much accuracy is high accuracy? I guess it depends on the data set and on your training environment, and sort of how does it stack up against other methods in that environment.
So I think it's quite difficult to put one number on that, right?
Yeah,
it's relative to your problem.
Yeah, so it's like, if you think what's high accuracy for MNIST, well, ideally 99.9 something is acceptable accuracy for MNIST. If you think about some other data set which has not been solved, then maybe the accuracy, the expected accuracy there is lower.
Cool. And I think Joao was just sort of making a similar point to what we just said. It's particularly useful when you compare estimators.
Yep.
Cool.
Yeah. So there's the Brier skill score. It's we presented that a little bit, but so it's a measurement that you can compare, that you can use, that you can calculate using the Brier score, that allows you to compare several different forecasters. So if you're thinking that several different things are giving you a forecast on the same event, you can fairly compare them using the Brier skill score, which is quite useful. And someone called Alan Mosca did a question in the Q&A. Is there anything in the... Oh, sorry, go ahead.
Is there anything in the paper about using the discordance in the ensemble to see how it relates to our distribution data? Not that I read.
Yeah, they don't mention that here. They only use the, I believe this is just a bagging method, and they measure the entropy on the ensemble. But so what Alan is hinting at here, or at least what I think he's hinting at, is that if you use ensembles, you can so you can use the difference in activations in the different methods. You can use it to see if this is actually in distribution uncertainty or completely out of distribution.
Right.
So it is something that is possible within the ensemble framework, but they don't use it here. They just measure the uncertainty in the method through the entropy of the final distribution of all the members.
So might the idea be, if you're seeing a sort of flat prediction across all of your models in the ensemble, then they're in distribution uncertain. Whereas if you're seeing lots of different shapes of your probability vector across your ensemble, that might refer to something else.
I think your microphone is a bit phony.
Oh, sorry. Yeah, I guess is the question, are the shapes of our softmax activations the same across our different ensembles? Is that, I think that's what I was asking. And I don't think they talk about that in this paper. No. Cool. And Alan says, I guess discordance would correlate with entropy too, though.
Yes, your microphone sounds very strange, Dan. It's like a robot voice. Didn't know there was an extension to the Brier score for non-binary events. Yes, you can define the Brier score for multi-class. Oh, well, not multi. Yes, multi-class classification problems. I think that the generalization is in the Wikipedia page for the Brier score, or at least that's where I found it last time I wanted to apply it. But yeah, it is generalizable. And maybe following up on Alan's question that discordant would correlate with entropy too, though. Yes, that's true. And but I think what we've seen from previous out of distribution, in distribution papers is that you can actually leverage ensembles to make a clear distinction between in distribution uncertainty and out of distribution uncertainty. I don't know if that is through the discordance in the members or with more structural analysis of how the activation paths work in each member of the ensemble. But it is possible. The only, I think in the uncertainty estimation literature, they are always pro ensembles, always citing the caveat that it is expensive to get big ensembles, which nowadays I'm not so sure. I mean, especially given that this paper says that 5 members is already enough. So I guess depending on the size of your model and the size of your data, it can get quite expensive to train 5 random initializations.
Is my mic back now, or is it still bad?
No, it's still bad. Sorry. Okay, so are there any more questions about the paper, comments that anyone would like to say about the paper?
I did just want to call out, I might still sound like a robot, but there is a GitHub page.
Yes. So yeah, the link for the GitHub is in the paper itself, and they're quite open about it in that they expect others to be able to reproduce their experiments, but also to use their code to test more models, which I think it's is quite interesting. So as Alan says, it's strange that someone publishes code to reproduce results, but yeah, it's a good thing. Sure. Uncertainty in regression problems. That's actually very, very interesting. Normally in regression problems, you do not have the problem of estimating uncertainty, because you can usually, so if you're calculating, if you're doing the regression problem, on inference time, you can estimate the error in your prediction as well. So the uncertainty becomes automatic. So if you're using, for example, a Bayesian approach, yeah, so, okay, if you're using a Bayesian approach for regression, you can just take several samples from the data generating process, and you will have a mean value and a standard deviation, and that already gives you the uncertainty in the process. The problem with uncertainty in deep learning is that is the problem of calibration, is that are you actually giving a true probability distribution or not? And well, how can you use that to estimate uncertainty? And what Joao put in the chat, the continuous ranked probability score, it's actually a very it's a useful metric, which is it's a generalization of the Breyer score. So it is what's it called? It's a true score in the sense that it can give you the accurate. It can give you an accurate estimate of the error of your forecast, and it works for both. It works for both classification and regression problems, in that if you simplify in one way, it simplifies to Breyer score. Yeah, a proper scoring rule, sorry. It simplifies to Breyer score, and if you simplify in a different way, it goes to mean square error, I think, which are both measurements of to rank the accuracy of forecasts. Do you want to try speaking, Dan?
Hello. Still bad?
No. Yeah. Still the same.
I don't think it's going to come back. So.
Okay. Okay. So
I think we've covered everything.
Okay. So